Hello, everybody. My name's Joe Kiniry, Carl. Kiniry. We'll get it right next time. It's all good. It's great to be back at the ERI Summit. I'm really happy to see friends and colleagues again face-to-face. I'm the extrovert that likes to be here. It's also great to be speaking again. I think Galois is 4 for 4 at the ERI Summit so far. You've heard some talks just a few minutes ago about scary things and troublesome things in the world of security. Threats that a lot of us, especially folks in industry, don't believe is necessary to worry about in a lot. And then we had this great panel that transitioned us and was reflective about the kinds of things that we can do moving forward. Locke has asked me to come today and be a bit more constructive and not play the scary guy, but instead be the constructive guy, telling you a story about one of our projects at my company called Galois that's gone on over the past few years that kind of hints towards this future of how do you build a system where your threat model, for example, says the adversary knows everything, knows every decision you've made, all your designs, they have your RTL, they have your software, and they have full access. That's the kind of environment we typically work in. Galois is an R&D firm. Most of us are in Portland. We're scattered around the world. We work a lot with DARPA. So today I'm going to talk to you about a project called 21cc, which was actually discussed in a presentation during the pandemic at a previous ERI Summit. And I'm going to give you a bit of an update on it and kind of a bigger picture framing. Galois is known historically in the old days as basically doing a lot of fancy crypto for the NSA and tools associated with specifying and reasoning about crypto and a lot of software. But about 15 years ago, we started doing hardware as well. And I've mostly led the hardware team over about the past 10 years for about half of my projects. Now, I'm going to be kind of critical of this community right now. Be warned, I first started doing hardware work when I was a graduate student at Caltech 25 years ago. At that point in time, we were hand laying out circuits. We were running SPICE. We weren't using HDLs. It was very old school. And of course, since I'm from Caltech, for the most part, we did asynchronous design. I then got out of hardware for a long time until I got back to Galois. And I started looking at the state of the art and what kinds of IP I was getting and how the tools worked, and I felt like none of it got very much better. I was very frustrated with what I witnessed. And I talked to companies that were coming into us to have them help work on or understand their own hardware systems, and they didn't even understand what they had themselves. And they were testing these systems, as we saw a testing talk yesterday, kind of like software was tested 20 years ago. And they talked about co-design, and there was really no co-design going on. Now, I'm broad brushing here. There are people who are doing really great stuff in each of these individual elements. But I saw a lot of opportunity, shall we say. And when it came to security, and you talked about security, you'd say, what's your threat model? And they'd say, what's a threat model? So that's where we started. And what's happened over time is that we've been asked to build a number of different either EDA tools to fit in holes in the market, or product demonstrations, or transition opportunities to try to take the sort of fancy things we do at Galois, which is basically applied formal methods for the real world, and make it usable and useful by normal engineers who don't know what a theorem is and what security means. We call this rigorous digital engineering. It used to be called something different until the government got excited about this idea and called it digital engineering, so we stuck a modifier on the front. And basically, it means building things using model-based engineering of various kinds with formal methods hidden behind the scenes so you don't see the equations. And in general, working on systems where you're doing correct by construction techniques, helping engineers make decisions that are verifiable as they take steps. This means in the general, anytime we build a new system, whether it's software, firmware, hardware, systems engineering, or a combination thereof, we're describing the system in an abstract fashion, using typically a domain-specific language of some kind. The project that I'll talk about right now is using a domain-specific language called Cryptol, which is the language the NSA uses to describe all crypto. Then we use tooling to automatically generate software, firmware, and hardware from these designs. And then we leverage traditional off-the-shelf tools, like EDA tools or software compilers and similar. But included in that mix is not just the generation of, say, an implementation, but also the generation of your entire test bench and your verification bench. So for example, out of the gate, you'd be doing simulation-based runtime verification of an ASIC design, as well as formal verification with Jasper Gold and other tools. The 21cc project was a solicited project from Ken Plax in about 2017, attached to the OMG program. What was desired at that point in time was a very flexible, high performance, low energy crypto module, or HSM, that did a variety of open algorithms that would be side channel free. And side channel free in this particular setting meant power and energy side channel free and timing side channel free. We have other programs that attend to other kinds of side channels. This was designed using a correct by construction flow, which I'll summarize in a bit more detail, and was fabricated at Global Foundries on their 12LP process. The project was unveiled at the ERI Summit 2020, and the government, this is now done, and the government is in possession of the equipment and evaluating the results, shall we say. Let me tell you a little bit about what it looks like. Firstly, in designing the system, we do so by doing that process I just summarized, writing a specification of the algorithms and how they fit together, essentially describing your system on chip as what amounts to a concurrent distributed system, because that's what an ASIC is. And by virtue of having that description, you automatically get a number of digital twins of the system, so you can simulate it at different fidelities with different performance. We then generate an asynchronous design from that particular specification in system Verilog, and also handwrite typically a combination of chisel and blue spec specifications to design the SoC. And then we're able to simulate and reason statically about that given design in those different languages based upon the specification we wrote. The nice thing about asynchronous design, or in this case a combination of synchronous and asynchronous design, is you get smooth performance power. You can run at threshold voltage correctly out of the box, but if you give it a lot of voltage, then it runs really darn fast. And in fact, based upon this flow, we got some of the lowest energy per bit encryption and decryption ever seen, better than hand-designed techniques. Working with our daughter company, Niobium Microsystems, we did a power side channel free approach to this that is reusable by others. That includes the idea of using island-based random dynamic voltage. Because we can change the voltage of any component of the chip at any point in time, we vary that voltage in a cryptographically random fashion across the entire chip as an additional measure to mitigate side channels. The throughput at various powers is excellent as compared to traditionally designed chips, and the number of traces necessary for disclosure is ridiculously high. We are now working with not only Niobium, as we continue to do so, but a few other firms as well. I'll mention a couple right now. PQ Security, who is here, we're working with on post-quantum algorithms. We've written formal literate specifications of all the post-quantum finalists, and NIST and NSA has those specifications, and hopefully those will be used, for example, for certification regimes from both agencies. And we work with RISCure on pre- and post-silicon analysis of side channels. And I encourage you to go see RISCure's demo later this afternoon. Our capabilities have broadened considerably over the course of this project and others, where we have to design new EDA tools to fill in holes, including those mentioned here, like information flow, timing leakage, automatically extracting architectures from hardware designs and software designs, product lines, and more. And so the typical artifacts that end up being created, sometimes written but mostly generated, associated with any given chip, are these, many of which were mentioned by the panelists earlier. You have to have a threat model. You have to understand your domain. You have to have a product line engineering model, because you're going to be reusing those resources over and over again to create new products. And the nice thing about all this recently is that we're packaging all these things together on a different DARPA project for Greg Cooperman as a digital ICD, a live living document that includes not just the normal things that you would expect to see in an ICD, English descriptions of what you're building, but formal specifications that can be used for these manifest ways. The few projects we're running right now that continue to use these same techniques and explore them and push them forward include Hyperspace for the SDA, which is ultra high performance, ultra low energy crypto for space use. Hardens for the Nuclear Regulatory Commission. How do we ensure nuclear power reactors that are going digital don't do it wrong? And Basilisk, which is for the DARPA DPRIVE program, where we're building a high assurance, fully homomorphic encryption accelerator using exactly this design flow. I'm hanging around for the rest of the day. We love to teach people about this. This isn't just our thing. We like to give it to others. Greg funded me to develop an entire course on RDE, which you're welcome to learn about and to take, for example. We're even thinking about just putting it online for free, because that's the right thing to do. Thanks for your attention. See you later.